morning, students. My name is Nanda Kumar and I am a teacher in chemistry. Today we start with the first chapter of the first year, Basic Concepts of Chemistry. As the very name implies, this chapter introduced to you the basic calculations involved in chemical reactions. So this chapter is important not only with respect to this chapter, but it is applied to calculations involved in the topics taken in other chapters too. Okay, so it is very important, and there are many subtopics in this chapter. Among them, we first take laws of chemical combination. There are mainly 5 laws of chemical combinations which are named here. First one is law of conservation of mass or law of indestructibility of mass, introduced by Lavoisier. He is known as the father of modern chemistry. Second one, law of definite proportion, otherwise called law of constant composition. It was introduced by Proust. Third one, law of multiple proportion, introduced by John Dalton. Law of reciprocal proportion or law of equivalent proportion, introduced by Richter. And the fifth one, law of combining volumes of gases, introduced by Gay-Lussac. Okay. Before discussing each and every one of these, first I will let you know some basic ideas regarding these 5 laws. The first point, all these laws were introduced before discovering atoms. Okay. All these laws were introduced before discovering atoms. Later, the ideas involved in these laws led to the discovery of atom. Okay. Ideas reflected in them led Dalton to introduce the concept called atom through his famous atomic theory. Okay. One of the law here is introduced by Dalton himself. So he, with the help of his law and also with the help of other laws, deduced this idea regarding atom. Okay. Then, at the time of introduction, these laws were empirical. Empirical law means what mentioned in the law can be proven experimentally, but the law may not be proven theoretically, or a theoretical explanation might not have been there. For example, the very first law introduced by Lavoisier, during chemical reaction, total mass of the reactant and total mass of the product are the same. It can be proven experimentally. For example, if you take 2 gram hydrogen, 16 gram oxygen and make them react under suitable condition, you may get 18 gram water. So 2 plus 16, 18. So you proved it through experiment. But if someone asks you why when 2 and 16 react, the product weight does not become 17 or 19. If you cannot explain that, the law is not theoretical. It remains as empirical. Okay. So at the time of introduction, these laws were theoretical in nature, but once or later when Dalton introduced the atomic theory, the first 4 laws could be given theoretical explanation. For example, the very first law, which was we discussing, total mass of the reactant is equal to the total mass of the product. How can we explain it based on Dalton's atomic theory? According to Dalton's atomic theory, one of the postulates states that mass can neither be created nor be destroyed, but only can be converted from one form to the other. So, if you apply that, you can very well say why when 2 gram react with the 16 gram, exactly 18 gram water is formed. So, then it becomes theoretical law. So, even though at the time of introduction these laws were empirical, once Dalton introduced atomic theory, based upon that, the first 4 laws could be given theoretical explanation. Why we exclude this law of combining volumes of gases? A reason is there. The first 4 laws, listen carefully, the first 4 laws can be applied to all the 3 states of matter: solid state, liquid state and gaseous state. This law, total mass of the reactant equal to total mass of the product, is applicable whether the reactants and products are in solid state or liquid state or gaseous state or in a mixed state. It is valid everywhere. Likewise, 2, 3 and before. But fifth law is based on volumes only. So it can be applied only to gaseous state. Okay, it cannot be applied to solid or liquid state. It can be applied to gaseous state. Okay, again, Dalton's atomic theory is based on masses. Dalton's atomic theory is based on masses, and these four laws are also based on masses. So naturally, Dalton's law could explain the first four laws. But Dalton's law did not connect mass with volume, and due to that reason, it cannot explain this law, combining volume. That law could not be explained. Anyhow, there is another gaseous law called Avogadro's law, which states that equal volumes of all gases at the same temperature and pressure contain same number molecule. Based on that, even this law can be now theoretically explained. So presently, even though at the time of introduction these laws were empirical, presently all have theoretical explanation too. So now we can move on to each and every law, explain them, and do calculations or problems involving the theory in these laws. Okay. We now start discussing the laws one by one. The very first law, law of conservation of mass. See, as per this law introduced by Lavoisier or Lavoisier, during chemical reaction, the total mass of the reactants and the total mass of the products are the same. Actually, the total mass of reactants reacted and the total mass of the product formed will be the same. Only that part you need to consider. You might have taken one reactant excess than required. That will not react. So, total mass of the reactant reacted will be equal to the total mass of the products formed. Okay. Or this law is stated in another way also. During chemical reaction, mass is neither created nor destroyed, but change in composition only. The substances may change, but mass will remain the same. You have to take note of one thing. It is specifically mentioned during chemical reaction. Now we know there are nuclear transformation, transmutation, etc., where mass can be convertible to energy. That is not applicable here. Only with respect to mass, the law is, chemical reaction, the law is valid. Okay. For example, see 12 gram carbon combined with 32 gram oxygen forming 44 gram carbon dioxide. 44 gram carbon dioxide. Okay. Even with this law, we can do problem that we will do later. Now we come on to the next law called law of constant composition or law of definite proportion. This law states that, it is introduced by Proust. This law states that the same compound always contain the same elements combined in the same fixed proportion by mass. The same compound always contains the same elements combined in the same fixed proportion by mass. For example, water. Water always contains hydrogen and oxygen in the mass ratio 2:16 or 1:18. We know 2 gram hydrogen combined with the 16 gram oxygen. So the water will be having this 2 gram there, this 16 gram there. So the mass ratio will be either 2:16, which is, or 1:8. That ratio will not be violated whatever be the way you prepare it or whatever be the way you isolate it. For example, you can get samples of pure water from different sources like rainwater or from well water, sea water, river water, etc. You take the sample after purification, take a definite mass, decompose it, collect the hydrogen and oxygen formed, and take the ratio. It will be always this 2:16. That is the content of the second law, which states that all compounds contain a particular compound contain the same element combined in the same fixed proportion by mass. Okay, this law has two names. Law of definite proportion means there is a definite ratio, or law of constant composition, which means the compound has always the same composition, constant composition or definite proportion. Definite proportion is with respect to reactant. The reactant masses have a definite proportion. Constant composition is with respect to the product. The product has a constant composition. Since the reactants have definite proportion, the product have constant composition. Thus the two names came. Okay. There are several ways of asking problems based on this, which we will come in the next stage. Okay. So we have explained theoretically the second law also. Again, one thing you have to take care. While you verify this law, different isotopes of the same element should not be considered together. While you verify this law, different elements of the same different isotopes of the same element should not be considered together. I will explain that through an example. Suppose you are studying with the H2O. One sample of H2O you taken, and there we will be able to prove that 2 gram combined with the 16 gram. Another sample of water you take, there also you will be proving that 2:16. Suppose you are given hydrogen, instead of hydrogen, if the water sample is having deuterium, then one sample will give you 4 gram deuterium and 16 gram water. Another sample of deuterium will give you 4 gram deuterium and 16 gram of water. So in the first experiment, two ratios were the same. So the law is valid. In the second experiment, two ratios are the same. The law is valid. But if instead you take one sample of H2O and another sample of D2O, in this the ratio will be 2:16 and here the ratio will be 4:16. Here the law will become invalid because you have considered different isotopes of the same element together. So when we consider isotopes together, this law become invalid. So we can apply this law only when isotopes are the same in both the samples. Okay, you have to remember that. Now we go to the third law. Okay, next the third law, law of multiple proportion. Here we deal with the two elements but forming two different compounds. In the law of definite proportion, we had two elements forming only one compound. Here we deal with a situation in two elements combined to form more than one compound. Say here we take case of two compounds. The law states that, it is introduced by Dalton. The law states that when two elements combine to form more than one compound, ratio of masses of one of the element in the two compounds that combines with the fixed mass of the other will be a simple ratio. I repeat, when two elements combine to form more than one compound, ratio of mass of one of the element that combines with a fixed mass of the other will be a simple ratio. You will understand that better while we deal with an example. For example, carbon and oxygen combine to form two main compounds. They are carbon monoxide and carbon dioxide. Okay. In carbon monoxide, 12 gram carbon combines with the 16 gram oxygen. In carbon dioxide, the same 12 gram carbon combines with the 32 gram oxygen. So, ratio of masses of oxygen that combines with 12 gram carbon. Here it is 16 gram, here it is 32 gram. So the ratio 16 is to 32 is 1 is to 2, a simple ratio. The law is justified. But we need not always restrict this study to take the ratio of second element combining with a fixed mass of the first. We may take even the other way. We can take the fixed mass of oxygen and find the mass of ratio of mass of carbon that combines with a fixed mass of oxygen. That I have done in the second proof. Suppose we take 16 gram oxygen as the fixed mass. Then this 16 gram oxygen is combining with the 12 gram carbon here. Agreed. Here 32 gram is combining with the 12 gram. So 16 gram, which is half of this, will combine with the half of this, that is 6 gram. Okay. So we can say that ratio of masses of carbon that combines with the 16 gram oxygen is 12 is to 6. 12 is to 12 by 2 is equal to 2 is to 1. This is again a simple ratio. Okay. Or we may even take 32 gram of oxygen as the fixed mass. Then how? Look here. Here 16 gram is combining with the 12 gram. So 32 gram will combine with the 2 into 12, 24 gram. Then ratio of mass of carbon that combines with the 32 gram. The fixed mass here is in the third example is 32 gram. 32 gram oxygen will be 24 here and 12 here. 24 is to 12 is equal to 2 is to 1. So again a simple ratio. So we may take either the first element to have a fixed mass and take the ratio of the second element's mass, or we may take second element's fixed mass and find the ratio of mass of the first element. Okay, both can be done. And we also find one thing. When we change the reference element, here it was carbon's fixed mass. Here it was oxygen's fixed mass. When we changed the reference, ratio got inversed. Here the ratio was 1 is to 2, whereas here the ratio is 2 is to 1. So when reference element was changed from one to the other, ratio get inversed. Okay. Further, for a given element, whatever be the standard mass we take, here we took 16 mass as the fixed mass. Here we took 32 gram as the fixed mass. Whatever be the fixed mass we take, the ratio will be the same. 2 is to 1, 2 is to 1. So, two additional things you have to remember other than the basic law is that when the reference element is changed, the ratio get inverse. For whatever be the mass we take as reference for the reference element, ratio will remain the same. Okay. This is the basis of law of multiple proportion. And here also the condition we mentioned for definite proportion is valid. That is, we should not consider two different elements of the same isotope together while we discuss multiple proportion. That's about law of multiple proportion. We have a variety of problems from this section also. We will see them later. So, the next law is law of reciprocal proportion or law of equivalent proportion introduced by Richter. Law of reciprocal proportion. In law of definite proportion, there were two elements and one compound. In the law of multiple proportion, we had two elements, two compounds. Coming to law of reciprocal proportion, there are three elements and there are three compounds. In such a way, suppose A, B and C are the elements, then the three compounds should be a combination between A and B, another one a combination between B and C, and third one a combination between A and C. All the three type combination must be there. Only in such cases law of reciprocal proportion can be applied. Now, we will see what this law states. Suppose element A separately combined with the element B and element C, forming compounds like AB, AC. And also suppose B and C combine among themselves too. So all the three combinations we have right now we have mentioned AB, AC, BC type. Need not be 1:1 more, atomic ratio. Whatever be the ratio, a combination between A and B, a combination between A and C, and a combination between B and C. Then first we take ratio of mass here, ratio of mass here. Okay, both ratio of masses. Then if the mass of A is fixed in these two compounds, keep the mass of A the same in both these compounds. Then you take the mass ratio of B and C. See, in combination of A and B, take the mass ratio of A is to B, and in the compound AC, take the mass ratio A is to C. Then take the mass ratio B is to C from these two ratios. When B and C combine, there will also be a ratio between the masses of B and C. Okay, let that ratio be x is to y. Then the law states that this ratio B by C, not A not included, B by C, and the direct combination ratio x is to y will be either the same or one will be a whole number multiple of the other. That don't say ratios will be same always. Either you get directly the same ratio or one will be the multiple of the other ratio, whole number multiple of the other ratio. Okay, or as a statement I can repeat, if elements A and B, if element A separately combines B and also with the C in the respective mass ratio A is to B and A is to C, then in a third possible combination between B and C, the mass ratio will be B by C or a simple multiple of it. Okay. I will repeat. If element A combined with the element B and also with the element C, in the respective mass ratio A is to B and A is to C, then in a direct combination between B and C, the mass ratio that we have written as x is to y will be related to B by C either through equality or one will be a whole number multiple of the other. That's the statement. That's the idea. When I make some example, you will understand it more. It is not very confusing. For example, we will see the case of carbon, hydrogen and oxygen. See, when carbon we have two proofs here. I am giving the first proof. Carbon combined with hydrogen to form methane. You can take any compound. For the time being, I have taken methane. Carbon combined with oxygen to form CO2. And at the same time, hydrogen and oxygen combine to form H2O. Now, we know in methane, mass ratio of carbon and hydrogen is 12:4. In carbon dioxide, mass ratio between carbon and oxygen is 12:32. So, hydrogen is to oxygen mass ratio that combines with a fixed mass of carbon which is 12 is 4/32. Let it be there. Now think about the third compound H2O. What is the mass ratio between hydrogen and oxygen in water? We know it is to be 2:60. The other ratio is 4/32. 4/32, 2/16. 4/32 is 1/8. 2/16 is 1/8. These two ratios are the same. So what the law stated is correct. Okay. Again, here the mass ratio 12:4. Here the mass ratio is 12:32. So we take the mass ratio 4/32 from here. We don't include 12 there. And we also take the mass ratio, direct combination mass ratio 2:16. And we see that these two ratios are the same. Now, in the second verification, I change only one compound. Instead of CO2, I took CO. Okay, CO. Now, here in methane, the mass ratio remains the same, 12:4. Here the mass ratio shows a difference. It is 12 is to 16 in the place of 12 is to 32. So the mass ratio of hydrogen and oxygen here 4 is to 16. Now in H2O the mass ratio is 2 is to 16. So one ratio is 4 is to 16, the other ratio is 2 is to 16. But if you multiply this ratio with the 2, both become equal. So this is a whole number. So again the law is valid, even though here we don't directly get the same ratio. By multiplying one ratio with a whole number, we get the other ratio. So here also the law is valid. Okay. So remember, definite proportion, 2 element, 1 compound. Multiple proportion, 2 element, 2 compounds. Reciprocal proportion, 3 element forming 3 different compounds. And these 3 different compounds should be in such a way AB, BC, AC. You cannot have AB, AB2 and AC. For example, you can have these examples, you know. Those which are not possible, I will tell example, CH4, C2H6, H2O. CH4, if you take CH4, C2H6, H2O, the problem is that we have 2 compounds from carbon and hydrogen and 1 compound from hydrogen and oxygen. But we didn't consider a combination between carbon and oxygen. So in such cases, we cannot apply this law. It must be very clearly understood that the 3 combinations must be in 3 different possible ways of combination. Okay, hope you got that right. Now we have the last law, the 5th law, called law of combining volumes, introduced by Gay-Lussac. Unlike the other 4 laws, which can be applied to any state of matter, such as solid state, liquid state or gaseous state, all the first 4 laws can be applied to any state of matter. This law can be applied only to gases. Okay, I didn't say this law alone can be applied to gases. This law can be applied only to gases. You must understand that way. Okay. According to this law, in a gaseous reaction, there exists a simple ratio among the volumes of reactants reacted and volumes of products formed. In a gaseous reaction, there exists a simple ratio among the volumes of reactants reacted and the volumes of products formed at a fixed temperature and pressure. It is the statement for the law. Okay. For example, in the reaction between hydrogen gas and chlorine gas forming hydrogen chloride gas, they found that for every 1 liter of hydrogen reacting with the 1 liter of chlorine, they got 2 liter of hydrogen chloride gas. All the measurements being done at the same temperature and the pressure. So the ratio of volume will be 1:1:2. Volume. In another experiment, when they reacted 1 liter or 1 volume in general, 1 volume nitrogen with 3 volume hydrogen, they got 2 volume ammonia. Like 1 liter reacted with 1 liter nitrogen reacted with 3 liter hydrogen, getting 2 liter ammonia. So ratio 1:3:2. This is only accidental. Here 1 plus 1 is equal to 2. It is nothing like that. It is very much evident from this 1:3:2. All the measurements being done at the same temperature and the pressure. Okay. So that much simple is the law. The law never states what will be the ratio. The law says that the ratio will be simple. They don't say this will be the ratio because it varies from case to case. Now, see, at the time of introduction of this law, the practice of writing chemical equations were not there. That's why I wrote hydrogen plus, I didn't use symbol etc. I simply wrote hydrogen plus chlorine giving hydrogen chloride. But now we know how to write a chemical equation. Now we know how to write chemical equation. For example, in the first case, presently we write 1H2 plus 1Cl2 giving 2HCl. Incidentally, the ratio they got at that time is nothing but the ratio of coefficients now we use to represent the same chemical reaction. The ratio of volumes they got then is nothing but the ratio of corresponding coefficients in the balanced chemical equation for the reaction. Here also it is like this. Look here. Here the ratio we know. The equation is N2, 1N2 plus 3H2 giving 2NH3. The ratio of coefficient is 1:3:2. Agreed. They got the same ratio from experiment. Ours is from looking at the chemical equation 1:3:2. Theirs were experimental, the same ratio. The theoretical ratio and the experimental ratios are the same. In all the cases it is like that. What is the logical explanation for this? See, I told you in the, I'm sorry, I didn't mention that even earlier. See, this can be applied, this can be explained on the basis of Avogadro's law. Avogadro's law is another law which you have to study. Avogadro's law is also a gaseous law. It can be applied to gaseous state only. It states that equal volumes of all gases under the same conditions of temperature and pressure contain same number of molecules. Equal volume of all gases at the same temperature and pressure contains same number of molecules. For gases there are only, we consider only 4 physical variables: temperature, pressure, volume, amount. In this particular statement, it is mentioned that same temperature, same pressure, same volume. If you are considering 2 gases, their temperature must be same, pressure must be same, volume must be same. Then it is quite natural that the 4th variable will also be the same. Amount means mole. So when temperature, pressure and volumes are the same, the amounts will be the same, the number of moles will be the same. When number of moles are the same, number of molecules will be the same. That's the content of the law. Equal volumes of all gases under same conditions of temperature and pressure contain same number of molecules. Okay. See, by applying Avogadro's law, we can explain why the ratio of coefficients 1:1:2 and the experimental ratio happens to be the same in all these cases. To understand that better, I am considering the case of ammonia formation. Listen carefully. Suppose at that time, when they were experimenting, they found that 1 volume nitrogen reacted with the 3 volume hydrogen, producing 2 volume ammonia, producing 2 volumes of ammonia. 1 volume nitrogen, they made react with the 3 volume hydrogen, and then they got 2 volume of ammonia at the same T and P, at same temperature and pressure. As per Avogadro's law, equal volumes of all gases contain the same number of molecules. Okay, suppose that number is small n, we take that to be small n. Then in the place of, suppose V contain n molecule. In the place of 1V, we can write n molecule. In the place of 3V, we can write 3n molecule. In the place of 2V, we can write 2n molecule. Then with respect to volume, this was the equation. With respect to number of molecule or number of mole, both are correct. It is NN2 plus 3NH2 giving 2NH3. N is a common coefficient there. You can cancel that. So what comes? 1N2 plus 3H2 giving 2NH3. Now we very easily understood why the coefficients in the chemical equation and the experimental ratio of volumes were the same. So the reason is that equal volumes of all gases contain same number of molecules. That's the reason why the ratio of coefficients and why the ratio of coefficient and the ratio of volume happen to be the same. So this law, you remember, can be applied only to gaseous state, and those and to chemical reactions carried out at a constant temperature and pressure. You have to remember. Again, one more thing you have to remember. See, suppose you are making react one more nitrogen and hydrogen forming ammonia. Suppose it reaches equilibrium. Then some nitrogen will be remaining, some hydrogen will be remaining, and some ammonia formed will be there. The law does not say about the ratio of nitrogen, hydrogen, and ammonia present at equilibrium, because the volume of nitrogen and hydrogen in that equilibrium is not that of the volumes reacted but remaining, and the law says that the ratio of volumes of reactants reacted and the volume of product formed will be simple. They didn't say that the ratio of volumes at equilibrium will be a simple whole number ratio. That the law never says. The remaining volumes of reactants and the volume of product formed need not form a simple ratio, because only during reaction such a simple ratio is maintained among reactants and the volume of the product formed. That must be borne in mind. Okay, only that much regarding Gay-Lussac's law of combining volume. Now we have covered all the 5 laws, and now we can go to solve problems based on this law too. Okay, so in our next stage, we'll start doing variety of problems. There are countless ways of asking questions. Okay, we'll do that in the next stage onwards. Okay. Our next problem from law of definite proportion. The question reads, what is the percentage mass of carbon in glucose? To solve this, we must know the formula as well as molecular mass of glucose. Glucose is C6H12O6 and its molecular mass 6 into 12 plus 12 into 1 plus 6 into 16, summing up to 180. So molecular mass of glucose is 180. And you want to know the percentage mass of carbon in glucose. If you look at this, we know that out of 180 gram glucose, 6 into 12 is the contribution of carbon. So out of 180, 6 into 12 is the contribution of carbon. In that case, if we take 100 gram glucose, how much carbon will be there? That will be the mass percent. So 6 into 12 into 100 by 180 will be your answer. 7200 by 180 is equal to 40. 40% is the mass percent of carbon in glucose. Okay. Now we can generalize this equation. Look, 6 stands for the number of carbon atom. I take the symbol N for that and suggest this number of atoms of that particular element whose mass percent you are calculating, and 12 is the atomic mass or gram atomic mass of carbon. So I write GAM, gram atomic mass, 100 is 100, and 180 is nothing but the molecular mass of the compound, means gram molecular mass. So you can make this equation by heart. Percent mass of an element is equal to number of atoms of that particular element, not total number of atoms. Which elements as percent you are calculating, it's a number in the molecule into gram atomic mass into 100 by gram molecular mass. That's the equation which you have to make by heart. Please remember, this equation is not alone to do this kind of problem. See, there are how many variables are there? This mass percent, N, GAM, GMM. It can be asked in 4 different ways. So, the same idea can be asked to find the number of a particular atom in a molecule, or the atomic mass of an element, or which element is that, to identify the element, or to find the molecular mass of the compound, or to identify the molecule. So, once you study an equation, there are variety of possibility of solution, means variety of possibility of asking questions. That you have to remember. An equation can be used in several ways to get several ideas. Okay, we will see one more. Okay. Now, from the second law, law of definite proportion or law of constant composition, problem 2. We give continuous number to the problems. Listen, the question is very simple. What mass of hydrogen is required to prepare 90 gram water? It's a basic question, very simple. See, while we solve problem from definite proportion, we must have some basic understanding. For example, to solve this problem, you must be aware of the fact that 2 gram hydrogen reacts with 16 gram oxygen forming 18 gram water. Actually, to get an answer, we are comparing our present situation with a standard condition. That is 2 gram combines with 16 gram forming 18 gram. Okay. So, by looking at, see one thing, if we are solving this problem, what will be our final step we are writing? We have this in mind. We will have this step as the final step. Therefore, mass of hydrogen required to prepare 90 gram water. Because that was what is asked in the question. So, we are actually having this last step in our mind first. Isn't it? We are having the last step that comes to our mind first. Then we will think how to get that. Then we will think about this step from this basic idea. See, since this step is mass of hydrogen required to prepare 90 gram water, the previous step will be identical to this. How? Mass of hydrogen required to prepare 18 gram. That is the standard idea. You know, 2 gram of hydrogen is required to prepare. Isn't it? So these two steps are identical because we are comparing one standard with the required. Both are identically presented. So by comparison, you get the answer. So from definite proportion, we get the answer mainly through such comparisons. So see, to get 18 gram water, you require 2 gram hydrogen. In that case, to get 90 gram. To get 18 gram standard, you require 2 gram. In that case, to get 90 gram, 2 by 18 into 90, 10 gram. So remember, this is the comparison way or equating two ratios. A by B is equal to C by D. Knowing A, B and D, you find C, etc. It is so simple. This is the fundamental idea regarding solving problems from law of definite proportion, and we can compare them just because according to this law, the compound always contains the same element combined in the same fixed proportion by mass. That's why we could equate A by B with C by D and find the unknown. Just because law of definite proportion is maintained, we can do this. It means that this solution is an application of law of definite proportion or law of constant composition. You got that? Okay.